Okay, hi again, everybody. Welcome back to the Escape School. This afternoon, we have Axel Donat that you met last week presenting Gammapy, the package for gamma ray astronomy. Axel, you can start when you want.
Thanks a lot, Thomas, for the short introduction. Okay, yeah, this afternoon we're going to take a look at the Gammapy package. In general, this is going to be a short session, so roughly one hour. So this is definitely not enough time to show like all the things that Gammapy can do. But I'm going to split this session into two parts. The first one would be like a general overview of the package, just introducing to you some of the main concepts and main data structures. And then the second part will be like a full gamma ray data analysis and actually show you how we can compute a spectrum of a source for CTA simulated data. In general, so if you want to follow along with the tutorial, this is the recommended way of doing it. So just execute the code cells on your local machine. Just make sure that you have updated the environment to include Gammapy. And I've written the command again to do this in the Slack channel. And of course, you can also use the Slack channel just to ask questions and comment. Okay, so what is Gammapy? Gammapy is a Python package for array astronomy. As its main dependencies to implement standard analysis methods for gamma ray data. So for data taking instruments such as HAZ, MAGIC, Veritas, or HAWK. And also Gammapy has been selected recently as the base library for the future Cherenkov telescope array. In general, Gammapy is structured into sub-packages. And my recommendation here would be just to go to the documentation, just following the link. So here on the left side, you can see the multiple sub-packages that Gammapy features, like analysis, access to data, makers, data sets. And in this lecture, we're going to take a look at some of them, but not all of them. So in general, like the documentation is a very good reference. This also counts for the tutorials in general. So you can, in here in the getting started section of the documentation, you can go to, there's really a large number of them. And then you can look for, let's say, like a specific analysis task that you want to achieve. And then you're going to learn how to do this with Gammapy. Okay, let's go back to the tutorial. So for the first part of the lecture, we're just going to use some Fermi-Lat data that was used for the free FHL catalog. And then in the second part, we're going to work with CTA, simulated CTA data. Okay, let's just start. So first, just the quick setup of the notebook. Here I'm just filtering out some warnings that I've recently seen with Matplotlib. Just as a comment, this is in general not necessarily advised. So if you filter warnings, this is something that you can do. But if you do it, make sure that you only filter like very, very specific ones. And this is just something that I'm doing here for this notebook. Then the second import here is on AstroPy. So as I've mentioned before, Gammapy uses AstroPy internally to handle coordinates and to handle quantities. And so if you're already familiar with those and have learned using those, for example, on Friday last week, then some of the things will be familiar to you already. I think the first interesting data structure that is used in Gammapy is the data structure of event lists. So all gamma ray data, actually independent of the instruments, at some point it can be represented just as a list of bare events. So for each of the events, you have measured, for example, the energy, the arrival time, and the arrival direction. And Gammapy has one core data structure to deal with this. So you can say from gammapy.data import event list. And then you can just create one event list by, for example, reading an existing one. And here, in this case, it's the one from, or a pre-filtered event list from Fermi-Lat 3 FHL, just containing some events in the region around the galactic center. So far, there's nothing this object does, but you can take a look at the actual data by accessing the .table attribute. This is something important to keep in mind. So in Gammapy, like all the data really just relies on NumPy arrays or table structures. And this also means if you're already familiar with those, then you can access the underlying data at any time, and you can do basically whatever you want with this. So if we take a look at the data, at this data table here, then you can actually see what the event list looks like. So for each row, it represents one event. And then you have a measurement of the energy, of the arrival time in right ascension declination, L and B for the formula theta and phi, zenith angle or azimuth angle. So a lot of additional information that you might not even, but the most important one is here, like the energy, arrival time, and arrival direction. Then, of course, just to check the total number of events, you can just length of the table and just say, okay, here it's like 32,843. So this is the total number of there, or if you want to get an overview of what are the quantities stored in this table, then you can just access the call names here. And then you will get an overview. So what provides Gammapy on top of this? And Gammapy provides with this event list data structure just some more convenience to work with this event list table. And this is in general true for many things in Gammapy. So in principle, you could just achieve everything with basic NumPy and AstroPy data structures. But however, this will just require you to write some more code. And in Gammapy, we've added some convenience layer on top. For example, you can directly access the energies of the events as a quantity and then convert to different units, as we've seen in the AstroPy lecture last week. Or you can directly access the sky coord object here and the position of the events, and you get back a sky coord object. And the same for the time. Then there's also typically some convenience for the plotting of the images. Let me just check back. So there was some error in the Slack, so saying not module named Gammapy. I think once you've updated your environment, I think this should work again. Okay, then there's also some convenience, for example, to directly plot the event. So you can just say on the event list object plot image, and then it will show an image preview of what the events actually look like binned into an image on a sky histogram. Another little use case would be to filter the event list based on region selection that you make. For example, you're only interested in the events given around, let's say, the galactic center. And for this, you can use an AstroPy affiliated package called regions. And from this, you can import an object called a circle sky region. And for this, you define a center of the circle just as an AstroPy sky coordinate. And then in addition, you define a radius for the circle. In this case, it's just 0.5 degrees. And then the event list object has a little convenience saying select region. And then you can pass in the region to this to make a selection on the events. And what you get back is, again, another event list. And then you could, for example, sort the resulting event list by energy. And then you could access the highest energy event here. And then you would see, for example, that in this case, the highest measured energy in the event list would be close to 2 tera electron volts, so like 1900 GeV. This is just a basic example of what you can do with a mixture of Gammapy and relying on normal, let's say, like AstroPy functionality. Another important data structure in Gammapy is what we call a map. And the map object is just a representation of a binned data structure together with some projection that maps the image coordinates to sky coordinates, typically based on WCS projection, but it also supports, for example, HealPix or other projections. So to create this object, this map object, we need to give some additional information. So we want, in this case, to create a sky map with the width of 20 degrees and a height of 10 degrees. Then the center of the map should be in the galactic center, so the coordinate that we've defined above. Then we're using a Cartesian projection for the mapping between the image coordinates and the sky coordinates. And we also use a pixel size of 0.05 degrees. This is specified with the spin size parameter here. And we also say we want to have a map type of using a WCS projection. And the coordinate frame that we're going to use is a galactic one. So this information is all stored in the map object. And then if you just print it on the screen, then you can see what this roughly look like. So it says, okay, it's an object called WCS and DMap. It is represented with this WCS geometry. It has two axes, so it has a longitude and latitude axis. And the shape along these axes is 400 and 200. And the overall dimension of this object is 2. So they're just two coordinate axes. You can also check this geom attribute just to get a bit more information on the actual geometry. But this basically just repeats the information that we've put in. So here's the long latitude axis. It uses the galactic frame Cartesian projection, and there it also tells you what was the center that you've defined and the width that you've defined. Okay, what's now nice about this already is it features a little convenience method where you can directly fill the event list into the map. So you're histogramming the events into the defined geometry here. And then you can directly use a little convenience method that is called .plot to plot the image on the screen. And this is what it looks like. It also provides a few more useful keywords, such as the stretch keyword here. So for example, if you're familiar with an image visualization tool, for example, such as DS9, there you can specify the stretch of the normalization to enhance weak structures in the image. So for example, if you would choose a linear scale, then it would look like this. And if you even choose a logarithmic scale, then you can see like all the weak structures in the images are nicely enhanced. And then of course you can also choose, for example, a color map of your choice. And internally, this again just calls into matplotlib. So if you're familiar with the matplotlib API, then you can pass on any keyword here and it will be passed on to matplotlib imshow. In addition, this also uses the AstroPy visualization WCS axis subpackage. And this we've talked about on Friday. This might be interesting later if you want to customize a bit the image plotting that we're doing here. Just to explain, so this map object also has a data attribute. And again, as I've mentioned before, this is just a plain NumPy array. So you can do any NumPy and operation on this, just in case, for example, it's not supported with the map API. What we can do easily is, for example, we can just sum up all the events contained in the image here. So we can just call gc_3fhl.data.sum, and then if we print the result, then this is what we get back here. Okay, this is only what we've used right now is just an image representation. But of course, we're actually also interested in like how does the data change with energy. And this is something that we can achieve with this map object as well. What we need there in addition is an object called a map axis. And this defines an additional axis to your map data structure. So what we can define here, just with this cell here, is a binning in energy. And there we say we want to create a map axis object from energy bounds. And what we are choosing here as a minimum energy is 10 GeV and the maximum energy of 2 TeV. So this is the energy range that was used for the 3FHL analysis. And it should contain 5 bins in energy. And now if we print this object, then you actually get a bit more information. So the name of the axis is energy. The unit would be TeV here. And then there's also a bit of additional information. So this interp keyword here is now set to log. And this actually means the bins in energy are logarithmically spaced and not linearly spaced. So this is like a very common choice if you want to analyze some gamma ray data, because of like the spectral dependency that you typically have for spectra is a power law shape. Okay, now we create actually a second map object, but in addition, we pass on this energy axis definition here. And this will create basically a three-dimensional data cube. So it's a list or a set of images varying with energy. We'll visualize this later, and then I think it's probably a bit more clear, but just to explain here. So if you print the actual object, you can see that there's now actually in the data structure an additional energy axis. Again, we can just use the same command to fill in the events. So you can just say, using this cube object here, .fill events, and then we pass on the event list. And then we can just, in addition, to make the structures that are in the image just a little bit more visible, we can actually smooth the image. This is also an operation that might be familiar to you if you have worked with DS9 in the past. And we're smoothing this image using a Gaussian kernel of width 0.1 degree. Now we can actually use the result of this just to visualize the map. And in Gammapy, we have some convenience method here that actually lets you plot this data cube interactively. So what you get in addition to showing the image here is a slider where you can actually slice through the energy planes of the image. So this is now the image in the lowest energy band. And now if you move the slider here, then it goes to higher energies. And you can nicely see how the data changes now with energy, and that at high energies, basically, you run out of statistics and you only have like a few events contained in the map. But this is very useful to interactively visualize the data and also debug. And this is like a good way of taking a first look of the data. And this is also a functionality that we're going to use later then for the actual analysis or full analysis. What can be also useful sometimes is just to visualize all energy planes in one figure. And this is done using this plot grid method. So instead of plot interactive, you can call plot grid and specify the number of columns that you want to use. But here we're using, again, just the same stretch and color map. This might take a second to run. And now we can actually visualize all the images in one figure, and you can take a look at all energies at the same time. What can be also useful in certain analysis is doing a cutout of this image. So for this, we also have some convenience in Gammapy. So there's a method called .cutout on this map object. And the important thing here is that all these methods that are defined on this map object, like smooth or cutout, those are generalized to these arbitrary extra axes. So if you call cutout, then the cutout will be done on all image planes at all energies. In this case here, we just define the center of the cutout. It's again just the center of the image, and the width of the cutout here should be 9 degrees. And this returns again back a map object, and then we can call again plot interactive just to take a look at the cutout. And now you've basically zoomed into the image of the center region here, and you could browse through the different image planes again. There's a more detailed introduction to this Gammapy maps data structure. I mean, this is only like a very small subset of what this can do, and this is, I've linked here in this maps notebook in the Gammapy tutorials page. Another useful subpackage in Gammapy is the access to source catalogs. So Gammapy provides some convenient interface to access and work with catalog-based data. And this is, of course, limited just to catalogs in the gamma ray domain. but there's support for multiple catalogs of those. One of those is the source catalog 3FHL. We could also import or go to the import here and then hit tab completion, and then you can see what are actually the catalogs that are all available. So there's 2FHL, the 2Hawk catalog, 3FGL, 4FGL is support for this Gammapy catalog, but also the Galactic Plane Story catalog. I think that's basically it, but I think these are basically the most important ones. The actual Fermi catalog, this is bundled in the tutorial or in the data of the tutorial. So we can just pass in the link here to the data file, and then it just reads back the data. And again, you can just access then the .table attribute, and what you will get back is an AstroPy table object. Here you can already see there's like 1,500 sources in this catalog, and then you can see like what's the source name, what's the position, longitude, latitude, confidence intervals for the position, etc. Now we can actually use this to do like a super small mini analysis. So we can sort, for example, this table by the significance of the source that was measured. The corresponding column name for this 3FHL catalog is signif_AVG, so the average significance averaged over time. And then we can invert the order of the table and take, for example, the top 5 of the sources. And then we can see like those are the 5 most significant sources in the 3FHL catalog. So it's the Crab Nebula, it's the Macquarian 421, it's the Vela Pulsar. So with this limited lines of code, you can already do, let's say, like a small analysis and take a look at the data and extract information that you're interested in. Gammapy provides, I mean, this example so far has just used AstroPy table functionality, but again, Gammapy provides some functionality on top. One thing is, for example, this access of the data by source name, so we can give any specified source name here. So, for example, the 3FHL identifier for the source, and then what it will return here as an object is a source catalog object 3FHL, and then you have access to all the data that is associated with this object. So for example, if we directly print this object, then you will get a nice printout of all the information contained in the catalog associated to this object. So for example, here's the source name. These are the associations to the object. This is the association probability. It says what's the class of the source. It's a BLL-like object. What's the significance? What's the highest energy photon? What's the redshift of the association here? And here's the position info. There's the info on the spectral fit of the source. There's also the information of the flux points here. This is already useful if you want to get like a nice overview of the information contained there. Then the actual data of this is then just stored as a dictionary on the object, and then you can of course just access any information here, for example, and work with it. For example, the information here, like this. Okay, what we can do now in addition, so we've created this image before, and now we can actually use some information of the catalog, for example, the position of all the sources, and plot the positions on top of the image. I think this is a very common thing to do. So we take the image that we've created before, we smooth it a little bit with the Gaussian kernel, and then we plot it, and then on top we just use matplotlib.scatter to put little crosses on the positions of the sources which are contained in the image. And this is what the result here looks like. So now you can see like where are other sources located. So this allows you already to do some visualization of the data contained and also like to do a bit of plotting. What's implemented in addition is some convenience to handle spectral models and flux points from the catalog. So let's just access another source here, the Crab nebula. So we're calling to the using the brackets here to access the information in the 3FHL catalog here. And again, we just print the returned object. Or actually, we're accessing a thing called the sky model object here first, but let me just also print the object that we have. So the and again, you will just see the basic info that is contained there. But then this information within Gammapy is translated into actual objects that you can work with. So for example, you can access the model info. Which is available as this sky model and then parentheses here. And then if you take a look here, this will then return a sky model object like so. And this sky model object then can be used again later, for example, to be fitted again to a different data set or as a basis for your analysis. But one can also do a few more things with this model information here, and this is what I'm going to show now. So in addition, so typically the sky model object here in Gammapy is a combination of multiple objects. So it can contain a spectral model, and then this is combined with a spatial model for the source and even possibly a temporal model for the source. So the underlying assumption here is that actually data and the model can be four-dimensional. So sources can vary with energy, with position, and with time. But it's also possible at any time just to work only, let's say, with a spectral model. And you don't have to necessarily define like the full complete model for any source. The most common thing is to work with the spectral model. And this you can access on the sky model object just as .spectral model. This is what I'm doing here. And then you can, for example, directly plot this spectral model on the screen using the .plot method, and they just specify the energy range in which you want to plot the model. And you can see here in this case, the best fit model for the Crab nebula here was just the power law with a given spectral index. So what we can also do with this spectral model object is we can, for example, compute the expected flux based on this model. In general, there are multiple definitions for fluxes in gamma ray astronomy. One would be the differential flux at a given energy. And this can be computed just by calling the spectral model object. So we pass in this energy here. And then we convert to the units that we would like to have. So this already tells you that under the hood, this returns an astropy quantity object, and then you can convert it to arbitrary units. So you could, for example, change to TeV here, and then you would get the exact same flux, but in different units. You can also evaluate the model at multiple energies, of course. You could pass in 300 GeV as an upper bound here as well. A second measure for spectral fluxes is integrated flux in a given energy range. This is also supported on this spectral model object with the dot integral method. And here you can give a lower and upper boundary for the integration here. So you're using 10 GeV and 2 TeV as the energy range. And then we just convert to integral flux units like this one here. So it's number of photons per square meter per second. And of course, I mean, you can easily convince yourself that this at least roughly corresponds to the value that is contained in the 3FHL catalog here. At the current point, I'm not 100% sure where it doesn't agree 100%. But for example, for complex or more complex model shapes, if it's not a power law, but an exponential cutoff power law, for example, then there's no analytical solution to this integral, and you have to rely on numerical integration. So this could differ in some cases. What you can also do, this is like a third measurement for flux. This would be the energy flux in a given energy range, and this is available as the dot energy flux method on the model spectral model object. And there you can give again an energy range here between 10 GeV and 20 G and 2000 GeV. What is also contained in the catalog as information are flux points to each of the source, and those can be accessed on the object just as dot flux points, and this will return a flux points object. Again, this is just a little convenience object to help visualizing flux points and to work with flux points in general. Just to mention it again, also the flux points object has a dot table attribute, and then all this information is nicely represented as an astropy table object, and you can print it here on the screen and take a look at what it actually contains. So as a final thing to do here, I would like to plot the spectral model, and then together with the error information that is contained, this can be done with the plot error method. And then also in addition, I would like to plot the flux points that are computed for the source. And here you basically have an SED plot that is commonly shown then in publications. But this is one way to access the information in the catalog and then to visualize, for example, the best fit spectrum model together with the flux points and many things like that. Okay, this was the overview part on some of the essential parts of Gammapy. Let me change to an actual analysis, but you will see that many of those concepts that I've shown here in classes will appear again then in the actual analysis. So let's change to the second notebook here, that is called Gammapy CTA-GZ. And this is just a little example analysis how to analyze CTA data. So right now, I mean, there is the first real CTA data taken by LST, but typically, or for a long time, they've been simulated data. And this is what we're working with right now. In general, you can use Gammapy to simulate data as well. And there are dedicated tutorials in the documentation. But right now, I'm just relying on this pre-simulated data just to make this a little bit more compact here. Again, we're just doing the imports here. Now this uses a lot of functionality that is defined in Gammapy. And this is probably a bit too much to explain everything in detail right now, but for now we just execute the import, and then I'm gonna explain some of the structures here in more detail, but you can also see that it also relies on some that we've seen already. The first thing to do for any kind of analysis that uses data from pointing instruments, so from for example, imaging atmospheric Cherenkov telescopes, is to make a sub-selection on the actual observations, and to basically also just access the data in general. And for this, the Gammapy has a dedicated object, which is called a data store. So it's a store that allows you to access the data. And this requires pointing the data store to the point where the actual data is stored. So if you want to analyze some real data with Gammapy, then you need to rely on the data being delivered in a special format, which is documented also publicly, which is called the Gamma Astro data formats. Let me just point you to the website here. I can share the link in the Slack as well. And this is the format that is used in Gammapy to access the underlying data. So if you're interested in some of the details, then you can take a look at this website here and read how those data formats are defined. So this is the main object here to get access to the data. And each of the observations from an imaging atmospheric Cherenkov telescope is associated with a unique identifier typically represented as some integer number. And here's just a selection of three observations that we're going to use. And those I can pass to the getObservations method to this data store object, and then it will actually return a list of observations here. We can actually take a look at some of the information here, or this we're actually going to do right now. So this data store object stores an overview of the observations called in this object called ops_table. This again internally relies on an AstroPy table object. But for example, you can select the ops IDs and then, for example, access some information here, like the ops ID, like what was the pointing of the instrument, pointing position in longitude and latitude, what was the lifetime of the observation, so how long did it take, and then you can see the information here. So typically in this scenario for the simulated data, the lifetime is basically always 1800 or roughly 1800 seconds. There are a few more little things that you can do. So we have created this observations object here, and this is also something that we can directly work with just to inspect interactively a little bit the data. So what we can do is we can access the data there just like a Python list, and we're giving the identifier here. Oops. In this case, I have to give it as a string. And this returns an object which is called an observation object. I think this makes sense. And then for this observation object, we can directly access all the data that is associated to this observation. So for example, we can access .events, and then you get back this event list object that we've seen in the first part of the lecture. And then you could also say, for example, what we've done before, plot image, and then this will already give you a preview of how the data is actually distributed spatially. There's a bit more that you could do. So in addition to the data, such as the events, of course, you need some more information on the instrument response for this measurement. And this is accessible on this object as well. For example, the effective area. This is stored in an attribute which is called ops.af. And then you could, for example, do a preview on the effective area for this observation. So you can call ops.af.peak, and then it shows you like how does the effective area changes with energy, how does it change with the offset of the observation, or offset from the center of the field of view of the telescope, and how does it change like with both. So here's offset and here's energy. The same goes for other instrument response functions, such as the point spread function, so the angular resolution of the telescopes here. So you can also call ops.psf.peak, and then it shows you how the PSF actually varies, or the containment radius of the PSF. So this is a measure for the size of the PSF, how this varies with energy. This is here shown on the right side. And this helps you a bit just to interactively explore a bit the data and work with this. But in the end, what we want to do is actually we want to create sky images, basically now complete ones, very similar to the simple exercise that I've shown before. So what we do is we define our analysis geometry or image geometry. So again, we use an energy axis here using dot from energy bounds. And this is created between 1.0 TeV and 10 TeV, and it contains 5 bins. And then in addition, we create the geometry of this map object independently and say, okay, it's centered in the galactic center. It should be 500 by 400 pixels, a bin size of 0.0. Comment here, you can always pass in an AstroPy quantity, but the default unit here assumed is degrees. And then we're also using a galactic coordinate frame. And then this looks again familiar to you. So this is what our 3-dimensional data structure looks like. Okay, now we can actually compute the images. There's some defines an API for this that lets you chain multiple data reduction steps. So this computing the images, this we typically call data reduction. So going from a plain event list to a bint histogram or a bint sky histogram, and also then to project the instrument response function actually on the same coordinate system. So to also project the instrument response on the same region on the sky. Here's an example how to do this. You don't have to understand all details here, but just like I'm gonna explain the general structure here. So there is on top of this map object, there's another object called the map data set. And this actually contains multiple maps with well-defined quantities. So a map data set has a counts attribute that contains the measured counts. It has a background with a background estimate. It also contains the reduced PSF information, and the same, for example, for the energy resolution. And the effective area is also translated into an exposure, so it's multiplied with the lifetime that later one can estimate the actual flux. Then this is the main data structure here, and then to create this, we're using an object called the map dataset maker, which will take then the observation and translate it into this map dataset object. And then in addition, this is a very common thing to do in ICT analysis. One can define a range of the data where it's considered to be safe, so where it's like a good estimate and a good knowledge, for example, of the instrument response. And a very common method to do this is to specify a maximum offset of events. And here we're specifying it as 2.5 degrees. Then one of the standard analysis modes is to stack observations. So typically for a given object, there are multiple observations available. And those observations are then just averaged. This means the instrument response is averaged between all the different observations by weighting it with a lifetime of the observation. And this is what is done in this loop here. And then finally, so I'm creating one of these data set objects per observations. Then I'm running this safe mask maker in addition. And then finally, I'm stacking everything into a single data set object. This will make a bit more sense once we can actually take a look at the images. Then I think this will be a bit more interesting. Just to illustrate this a little bit, so we now have this stacked data set object. This now contains, for example, the counts. And this is, again, just one of these map objects. So we can directly call .smooth, for example, as we've seen before. Maybe let's take 0.1 degrees. And then you can call plot interactive. And then we'll show you this interactive representation of the cube. And here you can see then how the data actually varies with energies. And here from this shape, you can nicely see the three different observations that we've chosen. So one was pointed here, another one was pointed here, and another one was pointed here. And in this final object, all the three observations are stacked into a single image. Just for the visualization again, I mean, we've computed this three-dimensional data structure, but we can also then directly integrate over the energy axis. And this is done with a little helper method called toImage. So this will take this three-dimensional map dataset object and reduce it to a two-dimensional one by integrating and weighting over the energy. So let's just take a look at the data here. So this is what the counts looks like. So this is now integrated over energy. Then there's also some estimate of the background in the same region. This is what this looks like. And if we now subtract already the background from the counts, then we get an estimate on the axis here. So this is these are the additional events measured over the background of this. And you can already see here in the center that there's actually like a nicely shaped source. So very bright around the galactic center and some diffuse emission around it. Then a very common thing to do and first step for once you've reduced your data is to actually detect some sources in the image. There are multiple ways to do this. A very common one would be to compute a significance map. This can be done in multiple ways. One way is to compute a so-called TS map. So this is a map that is very often used, for example, for Fermi analysis as well. And this TS map will actually fit a source model that you specify. It will fit this model at each position of the map, and then return the expected significance under the assumption of this model here. So what we have to do first then in Gammapy is that we actually define the model. So we say we want to look for bit extended sources. So we're taking here a Gaussian shape and a Gaussian spatial model. And in addition, we specify a power law spectrum model with a spectral index of 2, and then we group everything into this sky model object that we've seen before, that was returned from this Fermi catalog object. Then this can be put into this TS map estimator. So here we put in the model assumption and a bit more additional information, like what is the size of the kernel that we want to compute. So what's the support that we want to evaluate, that we want to use to evaluate the model. We can use a little bit of downsampling, so we can increase the bin size just internally to speed up a little bit the computation. And here we say we can sum over the energy groups optionally. So if you have, for example, a data cube, then you can directly compute the significance maps in energy bands. In this case, we're not doing this just because we put in the information already. And here is now the energy axis that we specify. Actually, I just realized, I mean, as we're passing in here only 2 energy edges, or only the single energy range, it's doing the fit just in this energy range here. Okay, then we just execute this TS map estimator by calling .run, and then we put in this stacked map data set. So this might run for a few seconds. So this is a rather costly operation. Okay, but it finished, let's say, in 8 seconds here. And now this returns a dictionary of maps, which is called images, or I've called those images TS, with some additional information. So it contains, for example, the flux estimate at the given position, the error of this flux estimate. It contains an estimation for the significance. This is named square root TS here. And it also contains the TS value. So right now this uses some of the nomenclature used by Fermi. So if you're familiar with Fermi analysis, then I think many of those are familiar. Many of those terms are familiar to you. If not, then you can always read about it in the Gammapy documentation. Okay, let's plot the significance image. So by accessing the square root TS image here in the dictionary and then calling .plot. And this is what the significance image looks like. Now you can actually read off already the significance here of the center source. So this is basically close to a significance of 40. Then to run the actual source detection, we can try to find peaks in the image. And this is just an example of a method. So this find peaks method here is actually borrowed from an AstroPy affiliated package which is called Photutils. And this shows a bit like how Gammapy interacts with other packages, and that you can always plug in, let's say, like external functionality to achieve a certain goal that you want to achieve. So we use this find peaks method here. We put in the actual data of the significance map. Then we say we want to work with a threshold of 5 sigma, and there should be a minimum distance between all the detected peaks of 0.2 degrees. What it returns is an AstroPy table object that you're already familiar with. with the actual value of the peak, and then the X and Y position in image coordinates, so in pixel coordinates, but also the position in sky coordinates, like right ascension declination. And then we can directly plot this on top of the significance image. And here you can see like where it detected those peaks, and those would be candidates, let's say, for example, new sources that you might want to detect in this field here. I mean, those sources are already known, but I don't know, maybe this one is a new candidate. It's simulated data anyway, but in general, this would be like the approach to do it. Okay, as a next step, we can actually do a spectral analysis. Sorry for this typo here. We can actually do a spectral analysis of the source. And for this, there are multiple methods available in Gammapy. So what we've seen right now was already working with a three-dimensional data set. A spectral analysis typically means reducing the data to a one-dimensional data set, so you're not taking into account the variation with position, but only with energy. And this is what I'm showing here. So as a first thing, we define a region where the data should be integrated. This is again just done using this circle sky region. Then we define a map axis again to define the energy binning. And then here we're doing additional things that we're also defining a second map axis, which specifies the true energy. So this is something to keep in mind. Of course, the energy resolution of all the detectors is limited. And a way to work or to handle this is with the so-called energy dispersion or energy dispersion matrix. And what is done in this case is that the actual model is evaluated in this true energy space, then the energy dispersion matrix is applied, and this will then transform the data into the reconstructed energy. This is done here, and now we can actually create not a map data set, but a spectrum data set, so just a one-dimensional data. This is just empty, but again, it contains the same quantities. So for example, there is counts now represented as a region ND map, which has a center and an energy axis here. We need to put in a little bit more information for this spectral analysis, and this means, in this case, an exclusion mask. So what we can do in Gammapy is we can do actually a background or an additional background estimation using some of what I would call like classical methods in gamma ray astronomy. The one that we want to use here is called reflected regions. I will explain it with a plot later what this actually does. But to exclude certain regions from this background estimate, we create this exclusion mask. And for this, we can rely on the same image geometry, so from this map object that we've used before. And there's a little helper method called .region mask, which lets you put in the definition of a region that you want to exclude. And if I execute this here, then can see what you get back is one of these ND map objects, but just defining the exclusion mask here, where the part in the center here, like this little region, this is excluded then from the background estimate. Now we can define this spectrum dataset maker, very similar to the map dataset maker that we've used before. And there's some additional configuration that we put in. For example, we can specify whether we want to do the containment correction. So this region is limited in size, and this means some of the events can leak out because of the point spread function, so because of the limited angular resolution of the instrument. And here we just say we only want to compute the counts, the exposure, and the energy dispersion. Then we want to use this reflected regions background estimate, and this just takes as information here the exclusion mask. And again, we use the same safe mask maker, just providing to define the energy range that we want to use. And this is defined by the point where the effective area actually reaches 10% of the maximum from the instrument. Then again, we have this data reduction loop. We run this spectrum dataset maker first. Then we run this reflected regions background estimator. Then we run the safe mask estimator, and then we append the data sets. So in this case here, we don't stack the data sets, so we don't average the data sets, but we keep all data sets in memory and just store them in this data sets object here. And as we've kept all the information of the individual observations, we can now actually plot some of the data. So we're going to use this image data set that we've created before, and we plot the counts. And then on top, we can visualize what the reflected regions background estimator actually did. For this, we have a little helper method called plot spectrum datasets of regions. And here you can see what happened. So the white circle here defines the region that we are interested in. And then the reflected regions background estimator estimated reflected regions around the pointing position for each of the observations to use this as a background estimate for the on region here in the center. And this was done for all the observations. This is nicely illustrated here with these colored circles. Okay, then to conclude the analysis, so we have now reduced the data into a spectrum data set. Now we can actually choose a spectral model that we would like to fit to the data. So we just choose a power law spectral model here with an index of 2 and an amplitude given in these units here. This is then bundled into the sky model object again. And then we can set the models just on this datasets object. So we can just say datasets.models equals model. And then we can pass this on to the fit object and we can call fit.run. And then it says like the optimization terminated successfully. And now if you print the model that you have defined before, then you can actually see that it now contains the optimized parameters, which are the best fit parameters to the data. Let's do one last thing here, so that we end up basically with the same plot that we've done for the simple exercise. Just for the flux point estimation, now we can stack all the data sets, and this is done with a little method called stack reduce on this data sets object here. You can actually also print the data sets. I haven't done this before, but this will show you some summary information on this data set object. So what's the number of total counts? What's the number of off counts? What's the number of expected background counts? What's the number of predicted counts, exposure, some further information. The dataset object also bundles the information on the likelihood for the fit and the actual fit statistic to use. And here in this case, it's called WSTAT. And this is the value of the likelihood after optimization. Let's do one last step in the spectral analysis. Let's compute some flux points here. And this is done with an object called the flux points estimator. This takes just the specification of new energy bins that you want to use for the flux points. And you have to tell the flux point estimator for which source you want to compute the flux points. So when we have defined the sky model object above, then we've assigned a name to this source. Here it was source minus GC. And then the flux point estimator can actually identify like for which of the sources we want to compute the flux points. Then we can call flux point estimator.run, and then we pass in just the stacked data sets here and run the object. This takes a few seconds here, and what we get back then is the table of flux points. So we have a reference energy for each of the flux points, minimum energy, and then the actual what's the actual DNDE, so what's the differential flux at the given energy, and a lot of additional information that right now I cannot explain in detail here, but you can always go to the Gammapy documentation to read about like what all is the additional information stored here. So let's conclude then with the same SED plot here. So there's a little convenience, so we can actually bundle the flux points and the model into a thing called flux points dataset, and then instead of plotting the information individually, you can just call flux points dataset.plotFit, and then this will give you the plot here. So it shows the flux points that we've computed as blue crosses here, the spectrum model, best fit spectrum model, and in addition also the error information shown as a gray band. And it also compares it then to the data by showing the residuals here. Okay, I think this is what I wanted to show. So it's already 3 o'clock. I don't know whether there's some time left for questions.
Yes, thank you for this introduction to Gammapy. As you said, it doesn't cover everything Gammapy can do, of course, but it will allow people to go have a look. We have maybe time for 1 or 2 questions. First one, a bit specific, but what does the containment correction do?
Yes. So containment correction is a concept that comes up for a spectral analysis that is based on a region. So if you assume that the angular resolution of the instrument, so the PSF or point spread function, is limited, then it has a certain size, and this means the events are actually have a distribution or have a probability distribution. And now, if you choose a certain region for a spectral analysis, which is actually smaller than the PSF, then there's like a non-zero probability that events end up outside this region. But if you know what the shape of the PSF is and the shape of this probability distribution, then you can correct for this effect. And this is called the containment correction.
Perfect, thanks. And a more generic one, maybe. Can you say a bit about FermiPy and compared to Gammapy? What can Gammapy do? Everything FermiPy can?
So I would say Gammapy, or the first or the most important thing to say first is, I mean, Gammapy and FermiPy actually have worked together in the past. So FermiPy also uses internally, for example, the same map data structures as Gammapy does. So this was a collaboration with the main author of FermiPy and Gammapy, like I think 3 or 4 years back. And then FermiPy is of course specialized to Fermi-lat data analysis, and I think it can only analyze Fermi-lat data. Gammapy is specialized typically to analyze data from Imogen Cherenkov telescopes, but you can in general also analyze Fermi-lat data, but only like in a very limited way. So typically it can only be high energy data, and there are certain optimizations missing, and there are certain handlings, special handlings of likelihoods missing that are in FermiPy. Gammapy is a more general package, but it can certainly not replace FermiPy. I think what's important to know for Gammapy, I mean, it was designed actually to combine or to be able to combine data from multiple instruments. So what you can do with Gammapy, for example, is you can use high energy Fermi data and you can combine it with data from Imogen Cherenkov telescopes to increase your statistics or to better constrain your measurement at low energies. And this is something, for example, I think that FermiPy cannot do.
Great, thanks. I had last question I didn't see before. When you run the fit and it fails, how can you check that the internals to see what went wrong? I usually get optimization failed, sorry, and I don't know why.
Yes, I mean, this is a very, very good question. It's also a very specific one. So, I mean, if you get back, for example, I presume like the person has used Gammapy before, and if you get back, for example, optimization failed, then one thing to comment here is, so Gammapy for the fitting internally relies on multiple backends. So you can use, for example, not only you can rely on SciPy Optimize, for example, for the optimization, but you can also rely on a package called iMinui, or you can rely on a package called Sherpa. So one thing to try would be just try different optimization algorithms. And at this point, I think I would just refer to the Gammapy documentation. So there's one tutorial in the Gammapy documentation that is called Modeling and Fitting. And this shows you a few ways how to check whether your fit actually converged, whether it's a reasonable fit, and how you work with different fit options. For example, you can store the trace of the fit and see where the convergence did go, or you can choose between multiple optimization options. Here's now the one using Sherpa. And here's also some information how to assess the quality of the fit, for example, by plotting likelihood profiles for each parameter. So if you've arrived at a good minimum, then you should see like a parabolic shape for each of those. Or I think you can also compute confidence controls to check the correlation between errors. So I think this would be a good entry point to debug somehow the convergence of your fit and get like additional information.
Okay, thank you, Axel. So that was the last question. We will stop here. Thank you again for this introduction on Gammapy. So we stop here for half an hour and we start again at 3:30 for the Scikit Hub introduction.
Thanks a lot. I'll be online in Slack now to answer further questions if needed.
Thanks.